Hello and welcome to today's Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. It's my pleasure today to welcome Samir Chanda to talk about E4S Extreme Scale Scientific Software Stack. Samir serves as the director of the Performance Research Laboratory at the University of Oregon and the president and director of Paratools Incorporated and Paratools SAS in France. It's a real pleasure to have you here today, Samir, and welcome you to proceed with your presentation.
Here in E4S, we provide both source-based builds as well as container-based deployment of popular HPC software packages. And our goal is to accelerate the development, deployment, and use of the HPC software, which is becoming more and more complex. So E4S provides these containers and stack-based source builds of a variety of different packages. These include packages from the MPI stack, such as MPitch, OpenMPI, development tools, performance evaluation tools such as Tau, HPC Toolkit, PAPI for hardware performance counters, access, and math libraries such as sundials, PETSI, Trilinos. There are data and viz tools that are available like Adios, HDF5. And we internally use Stack as the primary platform for software delivery in the E4S. We have SDKs, which are a collection of related ST products where coordination across package teams improves usability and practices. And these SDKs involve several different products. These are then used to create containers. And containers of pre-built binaries of ST products are available for download from the E4S website, shown here as e4s.io. We have got container images that are available for download from Docker Hub. We have support for different container runtimes, including Charlie Cloud, Shifter, Singularity, Inception from NCAR. And we also have an OVA, Open Virtualization Appliance of VirtualBox software that contains all of these runtimes. So you can try some of the tools such as Shifter within the VirtualBox image. We also use MPI replacement strategies to use native network interconnect. And by that, what I mean is, imagine an environment where you could build your application on your laptop and transfer it to a machine such as the Blue Water system and run the binary unmodified while taking advantage of the high-speed internode interconnect. So you could use the Cray interconnect and use the Cray the Cray MPI stack to run your application while getting the libraries from our E4S container. And if time permits, I would like to show you a demo of this. But first of all, what are containers? Containers represent a lightweight collection of executable software that has everything you need to run a specific application. It does not include the operating system kernel and is typically based on Linux only. So you can think of it as chroot on steroids. And Docker is a very commonly used tool which is available on many platforms and used widely in industry. And we have support for Docker in our E4S containers. Now, I would like to give credit for these slides on Docker and containers to Andrew Young from Sandia. And you can find out more about this tutorial that we just presented at ISC. So there is a distinction between hypervisors and containers. There are different types of hypervisor. There's a type 1 hypervisor that, as you can see, inserts a layer below the operating system host. And then there is the hypervisor type 2 that works as or within the host OS. But in a container, and this is where it is very different from VirtualBox or any other virtualization software, there is only one operating system, and the container runs directly on that operating system. So containers do not abstract hardware. Instead, they provide an enhanced CH root to create an isolated environment. And people are looking at containers as a means for reproducing software and scientific results. So all these solutions enable custom software stacks on existing hardware and user-defined images. And we'll focus on containers as far as this particular webinar is concerned. So abstracting hardware and software resources has had profound impact on computing. And we know about virtual machines and cloud computing from the past decade. And there are many examples. But OS-level virtualization is a bit different. And the performance with containers is fairly good. So people are looking at containers as a mechanism for deploying their applications on HPC systems. Now, in the cloud industry, you can see that containers are used to create large-scale, loosely coupled services where they are microservices, and then you just try to jam as many containers on hosts for increased system utilization. We'll not look at that case. We are looking at the use of container-based software for scientific computing on supercomputers. So for enabling developers to specify a user-defined software stack and their own software ecosystem, the US Department of Energy's high-performance computing resources need to support emerging software stacks, as do systems from Department of Defense and National Science Foundation and NASA. And we are looking at common solutions that will work across different HPC systems where we can package the HPC software and then deploy it in a easy-to-use manner. So the features for HPC, as far as containers are concerned, is that you can bring your own environment. Developers can define their operating system, libraries in which their application runs. You can compose these user-defined images and software environments with modular components, and then enable reproducible environments that can span different architectures. And we are creating solutions for that in the E4S. This can enhance portability. It can enhance the version control integration with systems such as Git. But container features that are not wanted in HPC include the overhead. So we need to make sure that the HPC applications cannot incur significant overhead from these containers. We don't care about these microservices, on-node partitioning, root operations, commodity networking. None of these are issues for HPC realm. But as far as containers for HPC concerned, we have found that Docker is not such a good fit for running HPC workloads. There are issues with security. They cannot allow root on shared resources. There's lack of HPC architecture support with batch integration. They assume local resources and commodity TCP/IP. But many solutions have emerged for addressing these needs for the high-performance computing solutions. And these include HPC runtimes such as Shifter, Singularity, Charlie Cloud. And we use all of these environments, and I will show you a demo of the use of E4S containers. Moving on, how do we build E4S? E4S is built using SPAC. SPAC is the primary package manager for software delivery. And SPAC provides the ability to specify versions of software packages that are interoperable or not. And then SPAC is a build layer for E4S containers, but also a large collection of software tools outside of ECPST. And you can use SPAC to install software on bare metal systems as well as create containers as we do in E4S. So SPAC supports achieving and maintaining interoperability between the software tools provided by ECP. And I would like to acknowledge Todd Gamblin for his slides on SPAC. So the motivation for SPAC is that scientific software is becoming extremely complex. You can see this in the dependency trees for different packages. Here is a tree for the application NALU, which provides a generalized, unstructured, massively parallel, low Mach flow simulation. And it depends on packages such as Trilinos, which brings in Parmedes, Boost, Mumps, NetCDF. And you can see that you need to configure and install these packages correctly for the full application to work. And here's another example, Deal2, the C++ finite element library. And you can see the complexity grow. Here is R minor. And very soon, all of these packages need to be installed correctly and configured in a compatible way. And this can become challenging for users. So SPAC is used to tame that complexity. We see that even proprietary codes are based on many open source libraries. Here is the Aries package, and you can see that it's using a number of tools like SciPy, NumPy, and Boost, and LAPACK, and OpenSSL, and MPI, HDF5. And half of this DAG is external, Blue, and more than half of it is open source. And all of this needs to be built specifically using a given compiler and MPI library on HPC systems to get the best performance. So the exascale computing project is building an entire ecosystem. There are over 15 applications. There are over 80 software packages. There are multiple architectures, including Intel, the PPC64LE. There is GPUs from AMD, from NVIDIA. We have laptops. We have ARM64 systems. And then there are several compilers, including Intel, GCC, Clang, PGI, Cray. There are different programming models. This includes OpenMPI, MPitch, the MPI variants, MVAPitch, as well as other programming models such as OpenMP, CUDA, OpenACC, Dharma, Legion, Raja, Cocos. And then there are different versions of each package and external dependencies. So this can lead to a combinatorial explosion if you want to install everything and test it. So every application has its own stack of dependencies, and developers, users, facilities dedicate many FTEs to just building and porting and maintaining the software. So that leads to a lot of issues, and often they trade reuse and usability for performance. So we must make it easier to rely on others' software and build the packages in a consistent manner. So if you recall, different solutions for building software, including like on a Mac since say 2013, where you say port install a library, it fetches the library, it installs the package, and this is just a package manager. But how do we install software on a supercomputer? So first, you get all the dependencies. You typically bring in all the tarballs, and if you're not using SPAC, you start building. And this includes, doing a configure with autoconf. You fight with the compiler. You track the configure arguments. You do again the configure, make install, and then you get a lot of these packages installed, and finally your application builds. When you run your code, if it seg faults, you need to start over again. And this is a complex process and not quite sustainable. So people may ask, what about modules? Well, most supercomputers now deploy some sort of module environments, and Tickle and LMod from TAC are the most popular ones. So you can, for example, if you don't find a compiler, you can just do a module load, and then you can load the compiler. But modules don't handle the installation. They are just this thin layer that allows you to set things such as path, LD library path, and dependencies with other modules. But somebody else has installed the packages, whether it's the compiler or the other dependencies, and you can only do a module load for things that you have installed. Now, containers provide a great way to reproduce and distribute an already built software stack. But somebody needs to build that container, and this is not trivial. And there can be several dependencies, and then there are issues with the operating system package manager or the dependencies on OS software stack. And there are various HPC runtimes, including Shifter, Singularity, Charlie Cloud, that can help with this process. But we need a more flexible way to build the containers in the first way. And so we use SPAC as the flexible package manager. And to use SPAC, you can just do a git clone like this and then set up the environment by sourcing the setup-env.sh. And then you're ready to install a package such as SPAC install HDF5. You can visit the SPAC.io webpage to see how you can download it and use it. But SPAC supports many different variants from the same build. You can specify different compilers, MPI implementations, or other variants. So SPAC provides a spec to describe the custom configurations. And each spec is used for a particular configuration. So let's say we want to install a package called MPI leaks. We can say SPAC install MPI leaks. Then we can use the app to use a custom version of MPI leaks. So we could say SPAC install MPI leaks at 3.3. Or we can specify a compiler. So we could say a compiler is specified with a percentage, and where you can say GCC at 473 version. So now you can see that SPAC is a package manager that understands versions, and it can understand compilers. You can also specify other build options like variants within the package, such as plus threads, where the spec of this MPI leaks package has described what threads means. So you can give a variant of plus threads, where the recipe for MPI leaks describes a variant of threads. You can specify C++ flags, which are then passed to the compiler. You can specify an operating system or target for a cross-compile system. You can also specify dependencies. So you could say, I'm interested in using mpitch if the recipe, for example, uses a default of OpenMPI, and you want to substitute the MPI. So you could say, I want to use mpitch at 3.2 with the GCC 493 compiler while installing version 3.3 of MPI leaks. So this provides a very natural vocabulary to then describe what package should be installed and what the dependencies and variants are for a particular configuration. SPAC list can show you which packages are available, and there is a large number of packages. There are over 3,000 built-in package recipes. SPAC find can show you what is installed, such as you click here and it shows you for this particular architecture in the GCC 447, you see all of these packages that are installed, or 482, or Intel 15, and so on. You can use SPAC to build packages on your HPC system, and it essentially simplifies HPC software for users, developers, cluster installations. It is central to the ECP software delivery strategy. And most of the ECP ST software is available through SPAC. So the roadmap is packed with new features for building ECP software distributions, better workflows for building containers, stacks for facilities, and there are optimized binaries, even binaries optimized for specific architectures, and better dependency resolution. Now, E4S uses SPAC for all the build of native binaries as well as container-based delivery. E4S being a community effort to provide open source software packages for deploying on the HPC systems, we have support for many different HPC environments already. We have done some initial testing on pre-exascale systems, such as Theta at ALCF using KNLs. This is a Cray XE system, the Cori system at NERSC. There are various systems from IBM, and these are Power 9 AC 922 systems. The Summit, Sierra, Butte, RZ Ansel at Livermore, and Oak Ridge National Labs. We have systems at Los Alamos, Sandia, Livermore, and even some NSF systems, including Frontera at TAC. And of course, the Blue Water system at NCSA, where we have done testing of E4S stack. Now, we are using E4S for preparing for future exascale systems, and we are testing on AMD and Intel systems as well. We have a release, a 0.2 release that we did in January of 2019, and it contains, over 37 of full release ECP-ST products. We have been planning for a release at Supercomputing 2019, and then we have support for several HPC runtime systems and just container environments, as I mentioned. We have also got E4S working on the AWS, on the Amazon cloud, and there is an image which is available for anyone to use without any royalty payments or anything. And this has been used in tutorials as well as used as a base image for the NASA Geoschem public image. And you can see the images that are available. You can just launch a particular image on AWS and just pay for the computer time. And essentially, our goal is to produce reproducible, customizable container builds and stack mirrors so that you can have an easy way to deploy the software that is being developed. And we have base images and recipes for building Docker-based containers on SDKs. You can see the E4S page on GitHub, where we have released recipes for building base images. And these base images include UBI 7.6, which is based on the Red Hat Enterprise Linux Universal Binary Image for x86-64. And UBI allows you to get support for the container when it is running on a Red Hat base OS. We have support for CentOS. We have support for Ubuntu. We have released base images for even IBM PPC64LE and ARM64. So we, in the E4S project, are providing build caches for SPAC for native bare metal as well as container-based installations of these products. And you can see the build caches at this web page. There is the E4S web page. There are Docker Hub base images that are available for download. And you can see different architectures under this ECP E4S. We have reproducible containers and their recipes. For example, this is the E4S for the UBI x86-64. And here is a stack.yaml file that describes that we should use the GCC 730 compiler with MPI variant with MPICH version 321. And then it specifies which packages to build in this case. And you can see the build caches, which store the binary release of a number of different packages. And this is a build cache that is for x86-64. So when you look at these packages, they are available for download, so you don't need to recompile it from source. And you can see that there are about 1363 stacked binaries in our build cache. And if you, for example, if you just click on a package such as Dynast, it will show you the full spec where you can find out more information about CentOS, Ubuntu, and you can see the full spec and hash and when it was built with what flags in which compilers and which dependencies like MPICH version 321 was used to build this particular package. So we have these build caches that are ready for you to use from our webpage. And then we can use this to build the products. Here is the screenshot of the build cache, and this is the URL. And the reproducible container builds using the E4S base image. So we have a GPG key that's installed in the build cache mirror and on the base image. So whenever you say spec install some spec, that checks in our mirror to see if that package is already available with the hash that matches. And then if it is, then it can just download that directly. So you don't have to rebuild it from the source. That can save you some time. And these are the reproducible base images for different architectures. You can search for ECP E4S on Docker Hub, and you'll find these base images on which you can make your own custom image. So that will save you a lot of time in creating an image which has MPI, compilers, and all installed. And we currently support x86-64, PPC-64LE, and AR64 for the ARM64 platforms. We have CentOS, Ubuntu, and Red Hat UBI support for base images. And here are examples of the use of the base image and the build caches, as I showed. Now, let me show you how to use the Docker image. First of all, if you want to use the E4S fully built image, we have a tag of Exascale project SDK AHM19 for the all hands meeting in January 2019. And we're also distributing this through USB sticks, or you can download the images from e4s.io. And typically you can just get a tarball, or you can pull it from the Docker Hub directly and look at Docker images. Now, what is interesting about this is that you can mount your home directory or your file systems within Docker, and then you can specify the image to use, and then it already contains stack, and you can look at a demo and see some examples over there. But this provides an environment on my laptop to use the image, and I don't need to install the compilers and MPI. They're all available for me to use. And to show you a demo of this, here is my laptop, and as root, I'm going to say run this image, and then after running it, just delete it and mount my $home directory as home smear and use this image. And I can get this. I can see which spec find will show me the packages that are installed. You can see all of these packages, and you can look at their dependencies. There is the dependency tree of Tralinos, and you can see it uses Boost and MPage and HDF5, and these are hashes for the particular example. You can say home smear demo. And here is an example, and I have a script where I can look at the location of Cocos, set this environment variable, export it, and then do a make. I can remove packages and then compile it. So Cocos provides a way to express parallelism efficiently in an application and provides the solution for the MPI plus X problem, where node level, the plus X part, is handled by Cocos, and it can map to pthread or OpenMP or CUDA or other node level parallelism constructs. So here I have built a package called lulesh.host, and then I can run it locally using this HWLock package that I load, and I'm running it just for 4 iterations like this. I'm also going to use tau to look at the performance of this application. And I can say run.sh. So what's important to see here is that Lulesh is an application that is outside of the container. The Lulesh Cocos application, it's using libraries such as HWLock or Cocos from within the container and other packages such as tau, where I can just say run with tau exec-event-based sampling to look at the performance. And then this is the dependency tree of Lulesh, as you can see. And all the packages that are coming from the E4S container, all running within Docker. And then just for a few iterations, I run the application, then I run it with tau. And without any modifications, tau understands the Cocos profiling interface, and then it is able to intercept the calls to Cocos, and then it runs the application. I do get profile files, and I can see the mounted directory and just launch paraprof as a, paraprof as the browser to look at the performance data. And then you can see the time spent in various MPI calls. You can look at the time spent in a particular Cocos construct. And here is the Cocos parallel for and the annotation in the source code. So, for example, if you look at the actual source code, you can see the parallel for and eval for elements over here. And you can see the parallel for construct where the user has annotated the source code and said, this is the parallel for loop, and given it a unique name that shows up in the performance data that's shown in paraprof and tau. So with this, I'm able to generate an executable. I'm able to analyze it all within the E4S environment. And moving on, here is an easy way for you to just have the full HPC environment on your laptop using Docker. Now, if we want to use a shifter at the NCSA Blue Water system, we should follow these steps. First of all, we must allocate a node. And here I allocate a single node. I specify shifter 16. Then I load the module for shifter, module load shifter. I pull the image. This needs to be done only once, and we have done it already. So it's available, this exascale project /SDK:H and 19. You'll see that the shifter syntax for pull is very similar to the Docker syntax. And then when you launch this image, you can say shifter -- image with this exascale project like this. And then you can unset the cray.pe version environment variable, load the bash RC, and then again, you'll find the same environment that I showed on Docker over here. So if I look at this, this particular file, I just say module load shifter. I have already allocated, in this case, 2 nodes with 32 MPI ranks per node, processes per node. And then I can say module load shifter, and I can specify this image. So here, if I say unset cray.pe version, and then source this etc bash rc, then on Blue Waters, now I can use the image in an interactive way. So here, after this bash rc is sourced, I will be able to then use, for example, spac find, and then see all the packages that are installed here. And there's a large number of packages that are available in this image. And we can do the other commands. So here I have the E4S image running in an interactive mode. I have come out of it, so it's back to the batch mode. And then you can look at Spec Find and see all the different versions. Like here we see Tralinos and Cocos and a number of these different packages. And you can look at the Spec location and then query the libraries and see all the other solvers that are present over here. Now, the interesting part with E4S is that I want to create an environment where I can build on my laptop and then run on an HPC system. So we are using the MPICH ABI for replacing MPI. So applications built with MPI in the E4S container can be replaced by the system MPI, and this allows us to use the fast internode communication using the native interconnect. So what we are saying here is that with the E4S container, the application and data are external to the container, while the programming models, compilers, runtime libraries, and tools are all in the container. And then we replace the MPI using this MPICH ABI compatibility layer so that we can build an MPI binary once and run it unmodified on different HPC systems while using their native network interconnect. So you could think of this as I could run this application on my laptop. I could run it on the Blue Water system using the Cray interconnect. I could run it with a Mellanox InfiniBand interconnect on a stock Linux x86 64 cluster for the same architecture. To do this, we first must allocate a node with the E4S image. So I have already done a pull, and I say allocate 2 nodes with 32 processes per node for this 1 hour, 15 minutes using the UDI of Exascale project SDK AHM19. So this user-defined image is then loaded with Shifter. And then we are using Shifter as the container environment. We have already pulled this image before using the Shifter image pull. And now we are ready to submit a job. So we have created a file called shiftermpi.sh, and we just modify the LD library path using this. And then we are able to load this in our bash script. So there are a few things that we must follow when we are using MPI to replace the MPI in the application with the Cray MPICH ABI package. I first of all do a module load of Cray MPICH ABI after loading Shifter and specifying Cray rootfs as Shifter, and then source this file, then set any library paths, and then set environment variables such as setting the number of threads and run the application. Now, I had just shown you a small test case on my laptop, and I built this image called lulesh.host. Now, what if I could take that same image that I built and transfer it? So here is the image that I just built, lulesh.host. And if I take this lulesh.host image, and I'm taking it to my University of Oregon system, and I'm transferring it over there. I ran that image over here with just 4 iterations. And let me try and get this image onto the NCSA Blue Water system. Now I've copied that same image from my laptop over to this Blue Water system. I have allocated a node, and there it is. So This is the image. And I have allocated 2 nodes, and I have a script called run.sh. Now, the same binary that I built using my E4S container is now going to run on the Blue Waters system. And we will be able to use 64 MPI ranks and replace MPI with the Cray mpich ABI package. And we will run it on 2 nodes, the same exact image, and a much bigger problem size, of course. And then we'll be able to use the E4S container in this manner. So there it is. And it ran successfully on the 2 nodes using 64 MPI ranks. It used 2 threads, and it essentially used the Cray MPI interconnect. So the same application binary can be run on my HPC system, as well as it can run on my laptop. You can see the size is the exact same size. And I have a viable way of using this in this manner. So I just run it like this and get the results. Now, I'll show you another example. If you're wondering, is it feasible to build an application with the container and then run it also? What is the difference in the time taken if I built an application using the host system and compilers and then compared it with what it would be like to run it with the compilers within the E4S image? So if you remember, I could get an interactive script like this. I can unset the Cray PE version, which kind of interferes with the modules environment from the Cray and what's installed on the container, and then load my bash RC file so that SPAC is in my path. And then I'll just go to, say, the mass parallel benchmark and say make. And here, if I say which MPI CC, it is loaded in my path from the container, okay? And you can see the MPI, which is loaded using SPAC. And I have this SPAC version of 321. I can say make. So now I'm using the compilers from the container. I'm using MPI from within the container. And I'm building this application, the NAS parallel benchmark BT, to run on, say, 64 with the problem size B. And it creates this executable. Now, this executable is available here. And I'll come out of the container and back to my regular compute node and go to this NAS parallel benchmark bin directory and run this application. Again, I specify Cray root FS as shifter. I load the shifter module. I already have the container, which is loaded with the UDI parameter. When I did the qsub to allocate a node, I used the same shifter mpi.sh to change my LD library path. And then essentially, I'm using app run. This is very important. I am not using MPI run. I'm using app run, and I'll specify 64 MPI ranks and run this application. Okay. So it will now use the mpich ABI to do the replacement and use the Cray native interconnect. So I just built the application within the container, and then I'm running it, and it says it took about 17.62 seconds. Now, if I take the same application and build it using the CC compiler and say make, then I'm using the Cray compiler such as FTN for Fortran, which uses MPI. I'm building the same 64-BT test case, and note that we ran it in 17.6 seconds total with app run. And I'll try to run the same application with the host-based execution environment without using containers, and see if there is a significant difference in the time to run the same application. Again, using 2 nodes, using the same Cray MPI environment and native interconnects. So here, if you look at the run.sh file, now I don't need to do any of those other things that I did before, so they all commented out. I'm just saying app run minus n64 and run this. And I have specified 32 processes per node when I did the qsub command. Like this, where I said 2 nodes with ppn 32, and then I will just look at this new BT binary that I created and then run it. Again, using time with the app run command. But this time, it's not using any container software. So it took 17.488 seconds total time. And if you recall, it is very close to the 17.62 with the additional overhead of using shifter and the container runtime. So you can see that the time taken for the application went from went up to 17.6 with the container, and here it is 17.48. So it's negligible difference in the use of the container runtime for building the application. Now, if you want to learn more about these tools and would like to try this on your laptop with the container environments, we also have an E4S VirtualBox OVA file where all of these runtimes, such as Docker, Singularity, Shifter, Charlie Cloud, are all packaged in a single OVA file, and you can download it from the e4s.io webpage and contact me if you'd like to have any help. You can also try the E4S image on Amazon AWS. These are the AMI, and please contact me for any passwords. So in conclusion, I would like to say that our goal is to increase the number of software tools and packages that we have in E4S. We want to port these packages and create containers and bare metal builds on IBM and ARM platforms, provide support for GPUs, visualization tools, add continuous integration and testing facilities. We want to deploy these stack-based mirrors and install the software using SPAC on bare metal on the HPC systems, as well as deploy the container-based runtimes, and then address scalable startup issues with full-featured supercontainers and improve the launch of MPI applications so it's seamless. So how can you get involved with what we are doing? Well, we would love to hear from you. Please come and attend our Birds of a Feather session at the Supercomputing SC19 conference in Denver. And we have a session, the E4S BOF on Tuesday, November 19th. We have a workshop, the first workshop on containers and new orchestration paradigms for isolated environments in HPC, also known as the Canopy HPC workshop at SC19. And it's on November 18th, Monday, from 2 to 5:30 p.m. and you can find out more from our webpage. And we also have a tutorial on Sunday, November 17th from 1:30 p.m. to 5 p.m. in room 201 at SC 19, the container computing for HPC and scientific workflows. So with this, I would like to conclude and thank the Exascale Computing Project for their support of this project. Any questions?
Thank you, Samir. If you have questions, go ahead and post them either on the YouTube chat or in the Slack channel if you're connected to Slack. While we wait to see if anyone submits questions, I have a couple for you.
Sure.
That's a long list of future activities. How do people keep track of how things are evolving? Is there a good place for people to look to track the activities?
Yes, in fact, our webpage, E4S.io, is a great location as a starting point. For project management purposes, we also have internal project web pages where Jira is used to track individual deliverables over time. And you will see a lot more of our images appear on our Docker Hub site, and you can track that too with the ECP, E4S, and Exascale project tags. And you can follow our progress as we add more container-based images for different architectures there.
And then if people want to get the hands-on and learn more, is there a good place to for training or other activities related to this where they can learn more in depth?
Yes. In fact, we have, besides these workshops and sessions at supercomputing, we can see that we have on our webpage an events tab, and you can see various workshops that we are planning. And for example, we had this workshop on NSF and DOE HPC tools at the University of Oregon. And we have the full videos of the talks and all the slides over here. You can see the entire day's videos for the SPAC tutorial that was conducted and different talks given at this workshop. You can track these videos and attend this. Does that help answer the question?
Yes, indeed. And then this feels like a very large effort. Can you describe who all is involved in the development and the support?
Oh, yes. There are many national labs involved in this activity, the E4S project, including Sandia, Lawrence Livermore National Labs, Los Alamos, and the University of Oregon. And Mike Hiru is the director of the project. And you can find out more about our team and contacts over here. So Jim Willenbring is the SDK lead. I'm leading the E4S, and Mike Hiru is the project leader for the ECP E4S project.
Excellent. I don't see any additional questions from the audience. So I ask everyone to join me in thanking Samir for this great presentation. We look forward to progress with this effort because I think it's going to be very valuable for the HPC community. So thank you again. And I'd like to let people know your presentation is a good lead into next week's presentation by Todd Gamblin on SPAC, package manager for HPC. So that'll be next Wednesday. We hope that those of you that were intrigued by today's presentation will follow up to hear more about SPAC from Todd next week. With that, we conclude today's webinar. And again, thank you very much, Samir.